Well, I think it's official. We can get started. Welcome back, everyone. On the Moodle website, we see our plan of attack for the day, but any questions at all to start us out? Okay, well, after getting through today, we'll take an entire week off. I think that's justly deserved. And then the week after spring break, the meetings will be continued to be in the classroom. I'll participate as the silent weird guy on Zoom again, observing how the next part goes. This will be about learning Python. And I think Python is a fantastic coding language. I'm pretty basic when it comes to coding. I've been living my whole life inside of RStudio, so I'm pretty excited about this part right here to kind of extend my horizons. But with our work we're doing today, we're finishing off this problem that we left off from last week. Sorry about the pacing. The pacing's kind of troublesome. It's hard to land and finish a problem on the day we started it. Then I decided to kind of break things up into a more smaller chunks so we're not just ending our last day with the problem hanging. This is a really fast hypothetical problem we'll go through. And this problem, we're mainly just looking into a larger data set. This one has about 600 observations over more than a couple variables, I think about 4 or 5 variables altogether, just to see what kind of exploratory statistical analysis we can do. And that's how we'll end the day today. Well, that's our goal so far. Any questions, comments, or suggestions at the moment? Okay, let's jump in then. So we left right here before we went on to the weekend. This was the solution we had so far to try to take on this problem above. So the readout on this problem is we put several people in a psychology experiment in a well-lit room, had them solve puzzles, probably pretty tricky ones. But the interesting thing about the study was we allowed the actual person being experimented on to self-report the number of correctly solved puzzles. So, for example, this individual solved 5, and that was the person's honest assessment. This person solved 12, and so on. They're also rewarded, they're incentivized to say that they solved extra puzzles, 50 cents per each. And the drama in the problem begins when we took the other half, randomly selected participants, put them in a dimly lit room, redid the same exact experiment, and now here are the number of self-reported correctly solved puzzles. Seems like it's a little bit higher just looking at the data. So we're testing this out with a set of hypotheses. We define the parameter mu w to be the number of correctly solved puzzles in the well-lit room. Mu d is the number of correctly solved puzzles in the dimly lit room. And formulating these hypotheses, we're about to do the statistical test. Null hypothesis is of no difference over here. Alternative hypothesis, we're checking in both directions that they're not equal. Maybe mu w is bigger or mu d is bigger, and this is allowing us to test in either direction. At a significance level 0.01 is the benchmark for evidence, which means we'll also output the confidence level. This one's set to 0.99. This part was us just doing some small exploratory statistical analysis just to see if the conditions were met. We saw evidence of there being some outliers by a rule of thumb. We saw evidence of skew, impactful skew. But the good news about the test we're running is that if the shapes of the data are the same, then we have more power and the conditions for t.test are even more robust. That's basically where we ended. We said conditions for t.test are met. We went back into RStudio and we wrote out this part right here. This is the whole analysis for our statistical problem. It's kind of weird that this is just us seeing if the conditions are met. And down below, that's all we have to run to actually do the t.test. I tried running the syntax when I loaded up before class even started, and I got an immediate error. But then I realized the problem. I never even loaded in the data. So if that's happened to you, that's probably what the problem is. Let me click on Import Dataset. From text space is the first option we'd select. We called it sample. Excuse me, we have the data called sample. But if you look at how our syntax is written, let's see here. We really looks like we called this puzzle altogether. So let's make sure we indicate the data frame in the same way. Call this puzzle. Might have been helpful if I named the actual data itself puzzle, so we didn't have to do that switch. But now here's the data frame re-imported. Clicking on the play button gives us the variables here. So 9 observations on 2 variables. And now with that input right here, we should be able to run this entire syntax. Hit Control A, Control Enter, and this is the output. We already included the graphics right here in our report, so this is more about this test right here. Notice it has a name, and what's important about this test is we never made an assumption that the variances in this group and this group are equal. So this is a nice test. There's no extra conditions we have to run through it. It tells us we get a p-value of 0.002581. Let's actually include this in the report as we analyze this. Also gives us a 99% confidence interval down below. And those were the main things that we wanted to finish off this problem. So just to give it a really fast final analysis, let's look into these key elements. We have down here a 99% confidence interval, as well as the p-value. Best way to take a look at this is let's carry down our hypotheses from above. Okay, so the p-value at 0.002581 is less than alpha. Let's say that right here. Less than 0.01, which is equal to alpha. And this implies we will reject H0. So there it is being rejected. It means we have evidence that this is true right here. If we were to write out a fast statement, we might say something along the lines of, the study provides significant statistical evidence that the average number of puzzles solved in the well-lit room and dimly lit room are different. So that's what the p-value is telling us. We have evidence that this alternative hypothesis is true. Any questions about that so far? Okay, when you really read that output right here, it is the output of the hypothesis test, and it's pretty much verbatim. We have evidence that these averages or means are different. And notice how unsatisfying that is. If you give this as a conclusion for your problem, and people are really interested in this conclusion, they have a follow-up statement for you almost immediately. The follow-up statement is, well, which one's higher and by how much? That's what the confidence interval down here provides. This is essentially a kind of follow-up analysis. We can now say down below, take our parameters from here. When we input them, we put well lit first. That means when the confidence interval was provided, it's really giving us this. The difference in means, well lit came first, matching this up. Dimly lit comes up second. And these values are constrained between those two figures. So it will be between negative 6.9 points if we round to the nearest point and negative 0.7 points. And so now if we see this estimate, that if we take the mean for the well-lit room and the mean for the dimly lit room, and it's always negative, that means this was higher on average. We can say, as a follow-up analysis, the average number of puzzles solved in the dimly lit room is from 0.7 points to 6.9 points higher than in the well-lit room with 99% confidence. So now we have essentially an answer to the question that yes, the average for the dimly lit groom was always higher because when we subtract, we only have negative values in our interval. If this was positive, our conclusion would run in a different way, which would be extremely weird because whatever conclusion you get from the confidence interval down here will match up the conclusion you get from the hypothesis test here every single time, provided it's a two-tailed test. That's one thing that's weird about statistics is there's other tests that make this analysis, which seems logical, kind of fall on its face. If we did a left-tailed test, the confidence interval analysis may not be the same as the hypothesis test analysis, unfortunately. But we did it, folks. The major objective with this problem was just to show if you're doing statistical inference, how would you make that happen? And the syntax is a great approach. Start with condition checking by giving graphics for the data. Then, once you know your conditions are met, end with just running the statistical procedure. That's what we did down below. We'll take all this, share it down below here. This is now the solution. Just a reminder on syntax. Word works really great for copying syntax out and bringing it into RStudio, but Word is the worst place ever to actually write in your syntax because certain things just don't format correctly, like those quotes right there by the red dot. Well, that's the wrap up of the problem that we left over the weekend. Next problem we're going to look into is just a fast application based on some prior work. But any last questions, folks, on our conclusions here? Okay, let me get this saved up. And like the other ones, I'll drop the results down below right around here, indented to signify these are the blank notes and the solutions right down below. Actually, just overwriting these ones down, these two down here. So now we're on to pretty much the last part of the course entirely. Let's go to the Snake River Bend farm problem. Once I get my windows in the right order here, give me a moment. Okay, here's the whole entire problem. The idea behind this problem is we did something pretty similar to this on our very first day taking a look into R. It was this problem right here. We were trying to find the area of a property. But when you do these kinds of problems, especially if you're doing them, say, for work, the trouble is if you do this problem well, people are probably going to come back to you and have you solve related questions. This could be like your specialty at your job workplace. So the syntax that we developed is right here, but really this is just a process. We're going to think of this as essentially one process from start to finish to handle any kind of related question if it keeps on coming up and up again. Here's that related question then. It says, it's all fictitious. There is no Mr. Johnson. I mean, there maybe is, but not necessarily who this is referring to. It says, Mr. Johnson owns a plot of land in southern Idaho near the Snake River. His property is roughly rectangular, so same sort of situation. However, it's bounded on the west side by Country Road 42, south side by Highway 78, and a small meandering stream, tributary to the Snake River, cuts across his property from west to east. Again, very, very similar problem. We have next information saying, forming the northern boundary of this arable land is that river. Mr. Johnson wants to precisely calculate the area of his cultivatable land to optimize irrigation, fertilizer application, make projections on revenue, all that kind of thing. And again, this is the role-playing side of it. Because you solved this problem so well, maybe he told his friends, you have more clients to do this kind of statistical consulting work. That's the idea behind this problem. So you're rehired. Now you're going to reanalyze a new problem. So here's the extra context. Mr. Johnson has survey data. There's measurements along the stream's path. It's not exactly a stream, right? It's a tributary. I guess it is a stream. They used a coordinate system where the origin is the intersection of County Road 42, Highway 78. So that, once again, matches up something like this right here. And next part they say is x-axis represents distance in feet, eastward along Highway 78. Y-axis represents distance in feet, northward along County Road 42. And we have 1,000 measurements to work with. We want to estimate the area of the property. So we'll just reuse this analysis right here. But we have to make some adjustments, right? This isn't going to work the same way because we have 1,000 observations. Really, that's 2,000 data values, x coordinate and y coordinate altogether. There's just no way we're going to type this in by hand. But still, we'll take this as a process. First, let's clear out the environment. I clicked on here to remove the variables. Just flush everything out. I've deleted the graphics, same button. I'm going to hit Control A and just delete to wipe out all of that. And this is the syntax that we worked on from day one, going into day two, admittedly. Let's now start by getting the data itself. We don't want all of that. The data is contained in a folder called coordinates in the Moodle website as well. So to import that data in a reasonable way, click Import Data Set from text base like before. I have my file here under coordinates. You should see XY indicated up here on top. If not, you might see V1, V2. You just have to switch headings to yes to make it look like that. That if your environment looks about like mine, just click on Import. Now we have the coordinate data. It's here in the data frame. It's also here just as a quick view of the data. Let's get rid of that so we can focus back on here. So we're redoing the same kind of problem, but not exactly. The purpose of this problem is to take what we've already painstakingly analyzed and just fine-tune this to take any set of coordinates whatsoever that matches that original problem. So first thing we'll do is here we'll say x gets. Our data is contained in coordinates, so just start typing that out. Relying on the code completion in RStudio is fantastic. Just let it complete. Hit the $ and grab the x coordinate. Same thing for the y variable. Next, go coordinates. $ select y. And that takes care of this block right here. Let's run just specifically that block and see how it handles. I'll click on Control Enter, and that should run just that bit right there. Yeah, it looks like it did. This is our plot, but it looks kind of wild. There's just a lot of values that's being plotted all at once. We can make another adjustment up here and write in PHC. That stands for point character. Ignore the P chi-squared. Set point character equal to, let's go in quotes. You could put anything you'd like here. You could put in a smiley face, but obviously that's going to be really disastrous for running this block right here. Can't even make it out. There's just too much data. Let me reset the environment. Let's put instead just a simple dot. That'll do the job. I just want to run this segment right here. Oh no, I cleared out my environment. Let me reinstall that. I need to remind myself not to clear out the whole environment each and every time. You know, the good news is once we adjusted this part to the syntax, we're all set. We can now just rerun it. And there it goes. That's a little bit better of a point character. There's 1,000 measurements, excuse me, tracking the tributary of the Snake River. It's kind of hard to see the individual dots because there's so many. But now we have a good view of what that actual stream looks like. So like before, we can jump down into just constructing a model. Usually when we are doing a bit of a model adjustment here, we want to start at linear and see how it changes at each new degree. This will put a line that hopefully goes to the data, matches it well. Let's see, what else do we have going on? We're also going to build the polynomial function. And thank goodness we did a loop right here. That means we didn't have to type this out verbatim. If for some reason we need like a 12th degree polynomial, Doesn't matter, it's just gonna loop through and really construct that for us. But down here, we would want to make adjustment with these values. Maybe the lower is always 0. Maybe the upper is always 400. Not in this problem. And I wouldn't want to make an adjustment just for this specific problem if we know we're reusing the syntax over and over again. What we should do is come back over here. Finding the area under the curve is just going to involve the minimum of x, the minimum of y. Actually, we could leave that right as is. Let's leave just this part alone and make the adjustments down here. Let's go min x gets, if we want the minimum, we just type out minimum and put in x. Let's test that out down below. Minimum x is 0 like expected. Likewise, max x is 1400, just like we expected from that graph. So there's the minimum, give it the max. And then down here, this is the integration step. We'll set lower to min x and upper to maximum x. Now, whatever coordinates we set in, as long as we know there's an intersection right there, that seemed like it was a big part of the problem. You know, that might not be too bad if it instead had data going off like this. I don't think we really needed the intersection down here around 1400 because our process is still going to give us some kind of polynomial going from 0, the minimum, whatever the maximum is, find the area under it. So it looks like the intersection here doesn't even really have to be a big part of the problem. Big part of the problem is just that the actual stream cuts through the whole entire horizontal extent of that property. So that seems to be the major feature. So that's why we'll always integrate from the minimum, always integrate from the maximum for related problems. And it seems like everything here should be in order. Any questions so far, folks, with any of those adjustments? Okay, I do sense one small issue. We're going to be putting a line on this, and our light is eventually going to bend. It might be actually kind of hard to see the difference between the line we produce and the actual data that we see right here already. Let's see if we can add just one more statement to this. Let's set color equal blue. Let me see if this is going to run well. Just want to run this block here. Yeah, now we have a blue line. So that's going to help us just discern the difference between the data and the model itself when it does the prediction. So I think we have a process. We took this script here, which we painstakingly built line by line, explaining each element. But really, this is just an analogy to the bigger problem. This is a better script because now we can import any kind of problem like this, just give it new coordinates, as long as it matches some of the key features. The stream has to go from left to right through your entire property, being the major feature. Let's run this and see what we get out of the whole output. Excuse me. So far, let's make maybe one big design change. Let's take the degree. This is something that we modify a lot in this problem, right? Let's put that right on the top. Modify the degree to find a well-fitted model. Let's put that right here. That way we can also kind of move up and focus on the output down below, less on all the syntax that we probably feel confident should run correctly. So now focusing on changing the degree, hit Control A, Control Enter. Everything has output. We have an area that looks like just over 1 million square feet. But what we want to take a look into is this figure right here. This tells us how well the linear model, this blue line that's plotted, is modeling the variation of the y data, how the second coordinates are rising and falling. It's doing a pretty good job, but when you look at the graph, you'd say probably not, right? I would say this area is suspect because sure, this has a high R squared adjusted value, saying it's handling a lot of the variation, over 90%, but doesn't really seem to be capturing the major feature about this tributary, that it curves a whole lot. We add curvature by increasing the degree. So let's go to degree 2. Major things we're watching for is, how does the R squared adjusted change? And how does the area change? Let's make some really fast recordings here just for the sake of tying this together. So let's put in a table with degree, area, and the degree was 1, giving an area of, let me just copy it in this way. Probably for a table like this, if we had additional time, you would probably want to put in the R squared adjusted value, just so you can see how things change as well. But that's the part we're going to look really carefully each time we run. So now degree 2 quadratic, hit Control A, Control Enter, let everything run. And here's our new model. Doesn't seem to be a huge improvement. At least there's some curvature to the blue line. So that's a bit of a help. And R squared adjusted has become 93%. That is a pretty good improvement. We can certainly do a little bit better, but just to see how things are changing, at degree 2, this is the new area figure we get. We want to make this as accurate as possible. So it helps to watch and see how these figures really change. Not much going from linear to the degree 2 quadratic. Almost kind of shocking, right? Slight increase in area. That's because the model itself only gave a slight bit of curvature in this range from 0 to 1400. We need way more curvature. There is one, well, maybe not major different turning points, but there's a lot of what almost looks like turning points through this. I would say degree 4 at minimum should be a good job. But let's walk our way up to it and see how things modify as the degree goes up. At degree 3, first let's grab our new area. Looks like no modification on degree 3 to the area. That's kind of curious. Let me double check that I really ran a degree 3. R squared adjusted value, it did go up. And we have the intercept, a degree 2 term, a degree 3 term. Let me double check. Oh, excuse me, intercept is the first term, degree 1, degree 2, degree 3. So it really is all there. Let me adjust this just a little bit so we can see that table better. So this is just a rerun in the same syntax. And I want this to be kind of formatted in this kind of way. Our adjusted R squared went up by a good amount, not a ton. And also, interesting things happened when we did this. Notice where it has the stars. That's where it's telling you that this term is significant. It should be a part of the model. When we went to degree 3, it says the degree 1 term is not significant in this. The p-value is really large, but all the other terms are significant. You also see it just doesn't seem to really fit how the data is working here. That's good enough evidence for us. We should go even to a higher degree. So now at degree 4, that's starting to look pretty good. The curvature of our blue line is really matching up with the black line here in a great way. Our area has changed in an appreciable way this time. So for degree 4, we're up to, I guess, not a huge change, but if we want to be as accurate as possible, it's encouraging that we see the line in blue actually modeling the data. Now we can be really confident that this is a better area computation for that property. Now we're asking ourselves the question, how high can we go on this? Let's go up to degree 5. Let's try to get this as close to 0.9999 as we can. And here's what changes at degree 5. Small area adjustment. On the right, the model seems to be doing even better. Actually, no adjustment on that. And looking into the R squared, it did go up by a good amount from the last one. We're at 0.9957. And oh, it's kind of hard to format this just right. Let me rerun the code just as it was. On the table, all parts of the model, every term, all 6 of them in the degree 5 polynomial are considered to be significant. Sounds like the model's performing well. Let's see if anything goes wrong at degree 6 and adjust from there. At degree 6, notice I don't think I can really even spot a difference between the data and the model. Even if I blow this up, let's see. Yeah, this is starting to get pretty close. The resolution, the pixel width of the screen I'm looking at this at is just not fine enough to really see a difference any longer. R squared has gone up to 0.9999. All terms are significant. That's really helpful as well. This would be a point where I would probably stop right here. The statistical idea is that there is a lot of value in parsimony, going for a model that's as simple as possible, that is as effective as possible. That's why we started at the lower degrees and worked our way up. This looks like it's a really good stopping point. We went to say degree something like 12 or 13, for example, run it this way. Sure, we get a figure out. Maybe the data looks pretty good, but look what's happening to the model. 1 star tells us degree 2 term is only barely significant. These values tell us the degree 9 term is essentially worthless. The scientific notation here tells us the numbers we're putting in front of x power 9 are essentially 0. And the p-values above 0.05 tell us that's not even a significant term in the first place. We're not trying to build a model that is trying to go from point to point and just draw a line crossing through every single point. We're just trying to model the actual real stream of the data, the actual real stream that is a tributary to the Snake River through the data. So we stop at the point where it looks like it's doing the best modeling possible. Right around degree 6 might be a pretty good choice. So let's walk this back to degree 6. Here's the now entire output. Let's see, what should we capture? Let's take this. Come down below here. We can now wrap this up and say, let me try one more little trick here. Okay, finally, we can wrap this up and say at a degree 6 polynomial, we can model the coordinates well, see syntax below, and the approximated area of this property is 1016,419 square feet. So we did it, folks. The purpose of this problem was supposed to go a little bit faster than it did. Sorry for the weird pacing. But the idea was RStudio is a great environment to not just write down a script and solve a problem once. It's a great environment to really just set up a process for something you're going to be doing over and over again. And there's really no limit to how fancy you can get with this. We're using just the base R package with RStudio, but there's loads of additional packages you could add on to this to improve the whole workflow in lots of interesting and creative ways. So we did it, folks. That's the fast analysis for just one more regression problem. And here's all of our modified syntax. Maybe you have to solve this problem again sometime in your life. This would be a way to go at it. But this problem is more about the analogy of just fine-tuning the script to line up with a process like we did. I think that's a good saving point for this one. Any last questions at all, folks? Running through that script the second time. Okay, last thing we want to take a look into is just a problem where we're purely looking into producing graphics. to ask and answer certain questions about data. So that's going to be the FEV data problem that you see right down here on the Moodle website. Loading it in, I've got it under, oh, wrong folder. Here it is. I have a file called cheat sheet, just in case I lose my way or we're running out of time. And we did get to a specific interesting part. The data is right here called FEV. It's a pretty large data set. There's loads of values here. The columns are mostly informative up to about that part maybe. And then the information here kind of fills in the rest. In the sex column, 0 will correspond to female, 1 will correspond to male. And in the smoke column, 0 will correspond to non-smoking, 1 will correspond to smoking. It just says provide some graphics for these data, but we should look into the context. This problem is all about the so-called forced expiratory volume. Probably said that wrong. The idea is you take a full breath of air, then you forcibly breathe out into a device in the first second after your full breath, and this is a way to measure your lung strength. If you ever got something like pneumonia, any kind of interesting condition like that, you might have had to have done this sort of measurement. So we have FEV data file measured in liters. For a large sample of children, this one turns out to be, making it a pretty impactful problem, along with some descriptions of each individual. So we have the age of each individual child, their lung strength as FEV, their height, this is in inches, their sex, and whether they smoked or not. It's nice seeing the zeros in there, but some of these children were classified in the smoking set. I don't know if that means that they're regular smokers, but I think what the study was all about is this child, for example, 9 years old, male, 1 means in the smoking group, probably exposed to secondhand smoke at home. Maybe some of the ones down below where they're teenagers might be actual habit smokers, like this 13-year-old. But I think there's a more to the definition of what we considered smoking in this problem. But let's give this a try. We're going to go to RStudio, import this data set right here, and just see what we can learn from the data. First, let's wipe out this environment. I usually just delete this right here and use this as my main script area. Also, we should delete this as well, just in case there's variables causing some conflictions. And this is leave out the prior graphics, less important. Click import dataset from text base. Find the file, the FEV one on the Moodle website. And this is what it should look like. Everything looks like it's set up. The variables are at the very top. If you see something like this, V1 through V5, then we've got a problem. But usually just clicking heading to yes is going to fix that weird error. Click import dataset. And now we have our 654 observations across 5 variables. Now all these variables are the same. First 3 are quantitative, but the last 2 are categorical, even though they are giving numbers. Their whole purpose is to categorize every one of the individuals as one of the sex or the other, and one of the smoking conditions or the other. Usually I click out the play button here just to get a better view of these variables, and here they are. The main problem is about lung strength, FEV. So if we had to produce some graphics, a natural thing might be to do hist for histogram, throw in FEV, hit Control-A, Control-Enter, and we get to our first error. One thing that's kind of frustrating about a data frame like this is you can't just give a histogram if there's 5 variables of mixed type as well. What we need to do is follow the indication here. When we click the play button on the data frame FEV, it reveals stuff that says $sign and then variable name. So if we come back over here, type a $sign, it's going to pop up a code completion block and just down arrow to FEV. Let's also add a little bit of extra elements to the graph. I want to go main, delete the main title. Then I want to go X label, give it an axis unit. So let's call this FEV in liters. And that's our histogram. Interesting features about it is it seems like the main peak is about between 2 and 3 liters for FEV. The data trails off to the right quite a bit, so we have right skew data. Not a whole lot we could say about that. Honestly, if I'm being completely honest, it's sort of a boring plot. We did want to take a look at it because it's part of the problem, right? It's the main interest in the problem. But if you plot just FEV, look at what it's ignored. Age data is gone, height, sex, and smoke data are gone. And smoke might be the second most important variable here. So let's still keep this as a screenshot. We can have good information about the main data set, the one variable. But we need to tell a better story here. If this is all we provided, then the researchers paid us to do this graphical analysis. They're probably going to be pissed off, right? Let's do a little bit better and start including the other variables in our graphics. So including another variable means the histogram might not be the best way to visualize this. Let's go to the box plot. We didn't say this too much when we used the box plot before, but one great rule about a box plot is that it can interact with categorical variables in a great way, and sometimes even quantitative variables like age as well. So let's go box plot, give it the data frame FEV, but hit $sign and select the actual FEV variable that we're going to be plotting. And then we use this little symbol. The tilde symbol is kind of a curious symbol because it comes back from when we were building a model. We said y tilde polynomial in x. This time we're saying we want a box plot of the FEV variable across the smoking condition. So go tilde, FEV, $sign, down arrow, and smoke. Let's add a little bit more to this. For this, we want to take for the Y label and make it be that same description. Y label gets, within quotes, FEV in liters. That's the graphic. It looks kind of ugly right here because of my limited resolution. If you have a limited resolution like me, click on export, copy to clipboard, and just kind of resize it so it's just easier to view what we're dealing with. I think that's a better resize in my opinion. FEV in liters goes this way horizontally, and the categorical variable goes, I said this weird, vertically this way, and categorical variable goes horizontally this way. Notice how jarring that is though. FEV $sign smoke is not something you want to include in your report. You could include this in your report though. Take a really refined screenshot and no problem there, right? But it's kind of a cop-out. There should be a better way to achieve that without having to take a super targeted screenshot like we just did. We do it by include an extra comma here, actually give it an X label. The categorical variable was smoking, so let's just say what the outcomes are to be specific. 0 is non-smoking. 1 is smoking. So last run on that box plot, we have a bit of a description now what's going on here. No weird artifacts from the actual R code syntax in our plot. That's one thing we definitely would want to eliminate. So now export, click the copy to clipboard button, resize it either which way that looks best to you. And this is still the screenshot I would take just to eliminate all that extra white space when we drop it in. So finally, here it is, folks. The FEV variable measuring lung strength in liters for the non-smoking group and the smoking group. Let's pause here for just a moment and look at each one of these elements. This line right here is an important line. That's the median. I'll just draw this in once, M for the median. The median is impactful for this graph because it's also the 50th percentile. We see some outliers as well. Looks like a good amount of them. going on the upper end. So the non-smoking group has a section of children that have really, really good lung strength. By the 1.5 IQR rule of thumb, all of those are flagged as outliers. But there's something really very odd about this plot. Anyone see anything that's almost disturbing when you really look at this? Let me add one more arrow here. That line segment, right at about 3 liters, is Q3, which is equal to the 75th percentile. Okay, well, this is a weird graph. It's almost disturbing in a way. If this is the 75th percentile, and this is the 50th percentile, then it's telling us in this group of children, the smoking group of children, we have about 50% of them with higher lung strength than, let's see here, the 25% of them right over here. In fact, if we were thinking in terms of medians, this one is about at 2.5. This one is about at, say, 3.1. This group is much higher. We did a statistical analysis on this. We might find significant statistical evidence that the children in the smoking group have higher lung strength than the children in the non-smoking group. And that just feels wrong, right? That can't be right. But it actually is. The data isn't lying to us. There seems to be really good lung strength for the children classified as being in the smoking group. Something is amiss about this. The data is right. Anyone see what could be an explanation or what new graph we should pull in? As you think about that, think also about these variables as well. We plotted FEV against smoke. I guess I can't highlight two things at once that way. Just double checking on the clock. One thing I've noticed here about this kind of problem is that it isn't easy to see why right away why there's a big discrepancy in this, where the smoking children seem to be performing pretty well. But when you think about this, when you really look into the data set, you might notice that the younger children are primarily the non-smokers. And when you get to the older children, they're the ones that looks like they're in the smoking group more often. There are some very young children in the smoking group, unfortunately, but it looks like what this is telling us is that age or height is a confounding variable here, a really impactful one. The older the kid is, the more likely they are to pick up smoking, but they're also just bigger children. Their lungs are bigger. And so that makes this a confounding variable. Same with height for the same exact reasons. So while this is the correct plot, it can give us the incorrect assumption about what's going on in the data. So we should follow up immediately with a better plot. So here's how it'll go. Let's do down below. Same sort of syntax, but we're going to do the FEV variable against, how about age? That kind of might make sense. Height might be a good one, but looking at the numbers, we have a lot of categories for their height, even though they rounded to the nearest half of an inch. Age group might be better because these are discrete integers. This is more like having discrete categories. So let's change this to age next. That means for the X label, this should just say age in years. Run this whole thing, and this is the new plot we get. This one's kind of hard to see unless we really adjust how this is being visualized. So this is the new graph. Some of these are kind of weird ones because there wasn't a lot of 3-year-olds, and you need 5 data values to fill out a whole box plot. So some of them collapse to just some weird little graphic anomaly. Other ones have enough data to really show. For the 4-year-olds, this is their lung strength. And as you go higher and higher, lung strength just goes up, as does the likelihood that you're in the smoking group. This explains the weird discrepancy we see in that prior box plot. But still a downside with even this graph is that it's only considering two variables at once. There's a way to do three variables at once if you really wanted to, and I was kind of concerned I might run out some time. This is what the three variable plot would look like. Let's see if we can import one of them, just to see what it would look like for our last analysis here. So for the three variable plot, what I've done is I'm plotting FEV against height. But I'm also including this weird little condition right here, an if-else condition. So I'm also including the sex as well for that categorical variable. If sex is set to 0, we'll give the dot a red dot, else it gets a blue dot, and syntax below just grabs a legend and puts it on there. This gives us a line through what's a scatter plot now, so we can see how the model is changing. And for our last graph, here is three variables at once. FEV versus height shows that the red dots are female, blue dots are male. As FEV gets higher and higher, the likelihood that you're just a taller person goes up and up. Kind of a weird plot. If I would have done this again, I probably would have put FEV on the y-axis and height on the horizontal axis instead. But sorry for the rush on that last problem there, folks. This 50 minutes are something I need to think about. They go by way too fast for me to actually get too deep into any one concept. Sorry for taking up time in weird spots. But any last questions or comments, folks, before we wrap it up for the day? Okay, well, I've certainly taken up quite a lot of your time. Thanks for letting me ramble on. I know it's kind of hard doing a class like this where I can't even see any of your faces. It's all over Zoom, but at least we've got a paper trail and a recording of what we did if you ever want to come back to that stuff. Have a great spring break, folks. I hope you don't have to work too much or not at all. And I'll see you all as the silent observer again when Mariam takes over the last part of the course. Have a great vacation, folks. See you all later.
Thank you.
Thank you.
Take care.